Let's do number 29 together, guys. The problem says you've got these equations and you're going to take the region that's bounded by these equations and you're going to rotate them about the x-axis. So if we rotate something about the x-axis, the equation is going to be v equals pi r squared minus r squared d x. We're going to rotate it about a horizontal line. Okay, so we're going to rotate it about the x-axis, and we may or may not have an r squared, a little r squared. So let's go ahead and figure out what this picture looks like. What you have originally is this happy face parabola, okay, y equals x squared plus 1 shifted up by 1. So if I find, let me turn off my sound. If I find 1 here, this parabola will look something that's like this, right? Y equals x squared plus 1. Let me move it over here. And then I also have another equation, y equals negative x squared plus 2x plus 5. That equation is a y equals x squared equation, so it's either going to be an up and down parabola, up or down parabola, and it's one's positive, one's negative, so therefore it's going to be a sad face parabola. And to find the relative max of this parabola, I'll just take the derivative of this. So y prime is equal to negative 2x plus 2 and set that equal to 0. So that would say 2x is equal to 2 or x is equal to 1. When x is equal to 1, y is going to be negative 1 plus 2 plus 5, which is 6. So that relative max is going to be at 1, 6. So let me go ahead and plot that. If this is 1, 2, 3, 4, 5, 6, and this is just an estimate. So come up here, got a point here, it's going to come down. Actually, where is the y-intercept here? When x is 0, y is 5, so this is 5 here, so it's going to come through like this. Gets a little bit better there, and then come through on this side like this. Okay, all right, so I'm going to find, take the region bounded by these two graphs plus x equals 0. X equals 0 is right here. Okay, so this wall over here, this part right here, so let me go ahead and highlight this part right here, I think. Let me get this point right here to see where x equals 3 is going to be. I don't know if x equals 3 is going to be the left of this intersecting point or the right of this intersecting point. See, what is this intersection? Okay, so the way to get that is to set these two parabolas equal to. So I'm going to set x squared plus 1 equal to negative x squared plus 2x plus 5. That gives me 2x squared minus 2x minus 4 is equal to 0. Take out the 2 and factor this quadratic. That gives me x is equal to 2 or x is equal to negative 1. When x is 2, y is going to be equal to 2 squared plus 1, so that's 5. And when x is negative 1, y is going to be equal to negative 1 squared plus 1, so that's equal to 2. Okay, so my points here, this point here is going to be negative 1, 2, and this point here is going to be 2, 5. Okay, if that point's 2, 5, then I know my x equals 3 is to the right of that. So x equals 3, let me draw it like that. So I'll put 3 here. And so this is my x equals 3 line. And so then my highlighted portion actually that I need to rotate is all of this yellow portion. These are the boundaries, and there's the region formed by these four equations, and so therefore I'm going to rotate this this region about the x-axis, which is kind of interesting because what is it going to end up looking like? It's going to end up looking kind of like a wreath or a knotted wreath or something like that, kind of a weird circular donut. It has a weird shape. Okay, so I've gotten those points. Let me clarify this. This point is 2, 5 right here. Okay, and let's go ahead and figure out what happens when I rotate these. I'm actually going to have to divide it into two different volumes. The volume, I think, of the left side from 0 to 2, and the volume of the right side from, what is this, from 2 to 3. Okay, so let me go ahead and do that. I'll do the blue side here and the black side for the right hand side. So on the blue side, I'm going to rotate just this region right here, just this left hand region. Okay, so the volume is going to be pi r squared minus r squared, and I'm rotating about a horizontal line, so that's a dx problem. Another way to know that it's a dx problem is when I find my capital R here, my capital R is going to be from the axis of rotation through the region to the furthest point on the region. That's my capital R. Let me draw a little bit better. Through the region to the furthest point on the region, and that's my capital R. So again, from the axis of rotation through the region to the furthest point on the region, that's my capital R. And if I find the length of this R, it's going to be y minus y. I mean, you can think of your R kind of like a Riemann-Sum bar. And so this Riemann-Sum bar is going to have a dx width. And it makes sense that with this dx width, this is going to be a dx. Okay? So the length of this R is going to be y minus y. The top y of this R is going to be this equation here. So this is the sad face equation. So this is going to be this equation here. Let me just call this y2, and I'll call this y1. So if I call this y2, this is going to be, this R is going to be y2 minus the y down here. This y is actually y equal to 0. So I'll call it y equals 0. I mean, just to make sure we understand, this big R is actually negative x squared plus 2x plus 5 minus 0. Okay, and I'm just calling it y2 minus 0. The little r is going to be, let me pull this thing out. Okay, so the little r is going to be from the axis of rotation to the region, not through the region, to the closest point on the region. So that's little r. Let me put my big R in so I can see this also. Okay, so my little r is going to be what I subtract, right? So I'm going to rotate this big function around. Then I'm going to subtract this hollow that's formed by rotating this little r around. And so the little r is going to be y minus y, because it's a vertical line, so it's y minus y. This y equals here is y equals x squared plus 1, and also that's called y1. So I'll say this is equal to y1 minus, the bottom y here is y equals 0, so y1 minus 0. I mean, another way to write it would be to write out the y1, so it's x squared plus 1 minus 0. Okay, so I've got my big R and my little r here, and all I would do is substitute in. So on the left-hand side, my volume is equal to pi r squared, big R squared, so that's y2 squared minus the little r squared. It turns out the little r is really just y1, so this is y1 squared dx. Okay, this is a dx problem. Okay, so that means these limits are x limits, and so in the region that I'm looking at right now, just the left-hand region, that is going to go from x value of 0 to x value of 2. Okay, let me move to the right-hand side, which is this portion right here. Okay, I'm going to rotate this portion here about the y-axis. I'm going to add that volume with the left-hand side that I've already gotten over here. Okay, so the right-hand side formula is going to be v equals pi r squared minus r squared dx. Okay, it's also rotating about a horizontal line. Okay, but now the capital R is actually a little different. Let's look at the capital R here. It'll be from the x-axis through the region to the furthest point on the graph. There's my big R. And what is the length of this big R? Okay, it's going to be it's going to be y minus y. What's this top y? This top y is y1 right here. Okay, so I can call it y1 minus this bottom y here is called 0. It's just y equals 0. So y1 minus 0. Or I could say, if I wrote it out, r is equal to x squared plus 1, okay, minus 0. And then let's look at the little r. The little r is going to be from the axis of rotation, not through the region, to the closest point on the curve, and that's the little r. And so the length of that little r, okay, because it's a vertical line, is going to be y minus y. This top y is this y here, which is y2. Okay, so this is going to be y2 minus, and then the bottom y here, if I drew a whole bunch of little r's, the bottom y is always going to be this y equals 0. So this will be minus 0. And another way to write this, of course, would be negative x squared plus 2x plus 5. Okay, so then I'm going to take these r's and I'm going to plug it into this equation here. So I've got volume here is equal to pi, this big R, which is really just y1, so it'll be y1 squared minus this little r, which turns out to be just y2 squared. This is a dx problem. If this is an x here, then that means that the limits here must be x values. So I look at my region here. This is my right-hand side. What's the smallest x value? 2. What's the largest x value? 3. And then what I'll do is I'll add these two volumes together, and that will give me the total volume. Now, I can do this easily by putting this into the calculator. Okay, so let me stow things into my calculator, and I think these will be easier. I'll just call y2 in my calculator negative x squared plus 2x plus 5, and I'll call y1 in my calculator x squared plus 1. So let's see how this turns out. Okay, get out your calculators, and turn it on. Okay, y1, I'm going to stow that as x squared plus 1. And y2, I'm going to stow that as negative x squared plus 2x plus 5. Negative x squared plus 2x plus 5. Okay, and what is that going to do? I'm going to, since I know I've defined these as y1 and y2s, when I call it up on my calculator, I can just use this vars button on my calculator. Let's see how to do it. Let's go to the home screen, which is second quit. Okay, I'm going to set this up as a math 9, and so I'll do math 9, and I'm going to go from 0 to 2. I do have a pi here that I'll take care of later, but that is 0 to 2. Okay, in here, this is just y2 squared minus y1 squared. So that's already stowed in my calculator, so I can just call out the y vars, okay, function, and I'll just pull out the y2 function, which is 2, and I'll square that. And then I subtract the y1 squared function. So again, that's vars, y vars, function, and then now pull out the y1 function, which is just 1, square that. Okay, make sure that you have a dx here, and then hit enter. Okay, and this answer right here, I can put it on the left-hand side, is 50.66666, lots of sixes, pi. Okay, so maybe I'll just do that or something, pi. Okay, and technically I should stow this, so let me go ahead and stow it, and I'll stow it as alpha A. Okay, so that means every time I push alpha A, now I'm going to get 50.667. So let me just put A right there because I've stowed it as A. I'm not stowing the pi, I'll just leave the pi there. I'm going to add this with the right side. This right volume is this integral right here times pi. So let me do this integral. So let me do a math 9. Okay, now this integral goes from 2 to 3. And the integrand here is y1 squared, so that's going to be vars, y vars 1, y1, and then square that, minus vars, I want the y2 now, so vars, y vars 1, pull out the y2, square that, okay, and I need that dx, hit enter, and what I get now is 4, let me do it in black, 1.6666, pi. Okay, and if I add these two volumes together, the blue volume here is the volume of the left side, the black volume here is the volume of the right side. If I add them together, and I'll get the answer. So I'm going to add this number with the alpha A that I've already stored. So alpha A. Okay, so the answer is going to be 92. Go 3 decimal places. Don't forget my pi. And there's my total volume.